Okay, we're on lecture 20, and we're going to finally wrap up our discussion on hash tables. Bit of a short lecture today, so I don't think we'll be here too late. But just a couple more topics I wanted to touch on. One, including primarily this idea of tombstones and what they mean and how we might delete them once we utilize them inside of our hash tables. I'll just mention that for, I think it was our last lecture, I think I got that one kind of messed up. Some of you might have seen it. So I had to replace it with last year's lecture for lecture 19, I believe, if I've got my numbers right. So I'll go back and double check, but I think I kind of botched the recording on that one. So apologies for that. Pretty much the same content, but if you see some of the dates, things looking a little bit strange in that previous recording, that might be why that's the case. I'll make sure it's clearly labeled so you know it's from the previous year, but the slides are updated. So sorry for that mix-up. That happens once or twice a semester just with all the buttons that I'm pushing up here. So let's kind of dive in. So we had our random programming lab due on Friday. We have an optional lab tonight. It's a fun one if you want a little puzzler. It is a primarily a linked list maintenance lab. It's a relatively common little puzzle, deleting every kth item in a closed ring of linked lists. So it kind of tests your ability to, continually decimate a ringed linked list until you get down to one node without crashing your program. So take a look at that if you want to. Like all of the optional labs, you have until the end of the semester if you want to do that to replace some other lowest grade, and it will kind of strengthen your kind of skills around doubly linked lists. We have our homework due on Tuesday. That's our separate chaining, and our quiz 5, which will cover our lecture today. So you'll want to maybe review a few of the things on today's lecture before you try that quiz if you haven't already done that. And always remember our Quizlets that are out there might help you as well. We're going to just talk briefly about tombstones, which is oddly appropriate for the Halloween area of our calendar. So this is what we do whenever we delete something from a open addressing type of hashing table. So we'll kind of dig into that briefly and talk about how we actually manage those things. We'll do kind of a roundup on performance and a few other odd topics before we kind of leave this and move into our next major module, which is working on graph trees, which is kind of a large part of the course. Quick review stuff. If you want to just in general up your understanding and acuity around the area of hash tables, do something like this. And I've been trying out both ChatGPT and Copilot. So we all have access to Copilot through Outlook. So if you go to your webmail inside of your College of Marin portal, you can click on Copilot and then open it up into full screen mode, and you have a full AI chat there. It's essentially based on OpenAI, so it's a different front end, but it's really driving the same back end, and it's kind of behind the firewall, so you don't have to log in with a Gmail or anything. You just use your College of Marin account. So it's actually not a bad way to go. But do something like this. Ask it to ask you questions. And it's actually surprisingly good at kind of covering a wide range of territory. So if you've got a little extra time and you just want to test yourself or up your understanding, that's actually not a bad way to go. And there are some things that it has done wrong. So I found it, I asked it to print some graphs for me, and it tends to get things swapped from time to time. So you have to pay attention to things if they look a little bit funny. It's not always 100% correct, but it's usually pretty good in the algorithms area for basic stuff. Remember that we have two kinds of hash tables: separate chaining, homework 5, open addressing, the musical chairs approach. That's your homework 5 one. And we're going to finish out this open addressing one today by just talking about this idea of adding and removing tombstones. Remember, I think I wasn't super clear on this. It's not a huge deal as far as your lab goes, but just remember that when we have a symbol table and a particular bucket is not empty, that means something is there. So if I have a key and I'm hashing it to a bucket location, if that thing is not empty, there's two possibilities. It might have the key I'm looking for already there, in which case we may need to update its value. Okay, so if the symbol table key stored at a particular bucket location is the key that I'm trying to store, then we just need to update the value. So we might need to go to the value component of whatever data structure we're using and update the value that's already there. So it's not exactly the same as a collision. It is a collision, but it's a collision with the key we're actually looking for. So if we are putting a key value pair in the table, usually that's what happens when we want to actually do an update. So you have an opportunity to do that, I think, on your lab or at least one of those practice problems we were doing. Okay. So I just wanted to mention that because I don't think I was very clear on that on our last lecture. Okay. Okay, and so just to round out the causes of cycling, we said if we're doing linear probing, the slope, if you will, the A coefficient on our linear equation there needs to be have a greatest common denominator with our table size, right? So I've got a B here, but it's really the coefficient and the table size. Greatest common denominator needs to be 1. That's what relative primes produce when we do the GDC for those two values. With quadratic probing, we just need to choose a form of quadratic equation that allows us to minimize the probing. And we kind of played around with method 2 here, but there's lots of them out there. And each one of them kind of comes with some other kinds of constraints that we need to pay attention to. We did not look together in class at double hashing. I will make sure it's not on any of our quizzes since we didn't have enough time to cover that one. But that's another pretty popular thing that you can do. It's a different kind of probing strategy. Our lab dealt with random hashing, which was another deterministic hash for those of you who looked into that. So those were just some of the ones that we looked at. And looked at some of the tricks we could do in code to sort of reset those values at various times. So today, primarily, I just want to touch on deleting keys to kind of round out this topic. So in the open addressing scenario, when we delete a key, it creates a unique problem. If we just remove the key from our bucket, then it leaves a gap that could undermine our ability to find other values that sort of probed over the top of those things that have now been deleted. So one solution is just to place a marker everywhere we delete something. We often call that a tombstone. And it's some kind of value or setting or, maybe a Boolean value in some data structure that indicates that, there's nothing there, but don't treat it as an empty space. We got to kind of keep probing over the top of that tombstone to potentially find the key that we're looking for. Okay, so now if we resize our array, our bucket, at some point because we've put too many things in it, that's a great opportunity to just throw away all the tombstones because we have to rehash everything anyway. So one, maybe good question to keep in mind is, what do you do when your table is full, when your load factor has basically gotten too high? Well, you just double the size very often, and then you rehash every key because the table size is going to change where those things go. You can't just copy it over into a different array in the same locations. So you will be writing that function as one of your homework 5 functions. So you might notice that thing come up if you haven't already tackled that part of homework 5. So remember, you're going to want to rehash everything in order to get it into a good location. Now, here's just an example of what happens if we don't do the proper thing with tombstones. If I insert a key, let's say in this case, we've got a really bad hash function here. So we're kind of binning things all in the same area. We're going to take some integer value k. So we're kind of hashing integer values, divide it by m, right, rather than modulo, and it's going to cluster a bunch of these objects all together. So hashing a 3 divided by 8, if that's our table size, goes to 0, right? So 3 goes there. 4 ends up essentially in the same place, right? So we get a collision at 4/8, and we got to add 1 to kind of move over. So now we've kind of put that next door, right? And do 5. And we get our typical kind of collisions when we have everything bunched all in one place. So now we've got these things in those consecutive positions. If I erase 4 simply and make that empty, and we come back and try to find the 5, we will actually never find it, because we will get to one collision, and when we probe forward to location 1, it looks like there's nothing there, right? So we stop here after probing off of the 3, and we say, oh, there must not be a 5 stored anywhere in this hash table. Okay, so normally we'll stop when we get to an empty place. That's the general rule when we probe, which is not the right answer, because obviously the 5 is right there. So just simply erasing one of these things from there is problematic. We've kind of got to put a tombstone in there that will, we can step on as we continue on searching for the 5. And if we get to another open position past the 5, then that means maybe that wasn't a 5 after all. Maybe that was a 6 or something. Okay. So we're still going to use our open positions as a way to decide when to stop looking, but we're going to leave some kind of marker in there so that we don't, screw up the search for everything else that's happened. Okay. Here's a way to delete the tombstones, or deleting keys, right? So we'll kind of come through here. We will erase the 4 and place some kind of value or some marker or indicator there in some way. And then when we come back to find the 5, we just sort of step on top of that one and keep going. Okay, so if we find a tombstone during the probe, we just kind of keep going. So that's our collision right there. Okay. So nothing too fancy about that. Okay. Now, at some point, like we said, we want to be able to remove the tombstones. We do not want to leave them in there long term, because it just sort of slows down our probing and it uses up extra space in our table. So what we want to be able to do is find a way to remove them at various times. So when we resize, perfect time to do that. So that's probably the easiest way to do that. Now, you will not be, of course, dealing with the rehashing and tombstones in the open addressing. This is, or in the separate chaining for homework 5. We only deal with that in our open addressing situation. Okay. But we do need a rehash, because the modulo times the table size is how we place our keys into the table. So when the table size changes, that of course means everything needs to be put into a new location. Okay. So there is a way to slowly, in a lazy way, get rid of these tombstones. So one algorithm is to say, on the way to finding a 5, right, if we pass over a tombstone, remember its location, and then once you find the 5, if you find it, move the 5 into the location of the first tombstone. So we're sort of collapsing down one of those tombstones, not the most recent one, but the first one we ran into after our initial hash location. So as we go forward, searching for the 5, we find it. We want to bring the 5 back over to that location. And then we want to zero out that position where the 5 was, essentially turning it back into an empty bucket. So we'll see this kind of strategy in some other data structures that we're going to look at, specifically one called union find, if we can fit it into the class. And it's basically the idea that you sort of do cleanup when someone asks for something and you go looking for it. That's an opportunity to maybe clean up a mess that you had made sort of previously. And that's essentially what's happening here. Once we find something, we take the opportunity to do some compaction. Okay. So that's going to do that progressively. Now, just again, to restate it one last time, we got to remember when we resize the tables, we may need to recalculate some of our constants. If we're doing linear probing and we're using a slope for our linear probe, the ideal slope is going to change because we've actually changed the size of our table. So we may need to recalculate that in an open addressing situation. Okay, not a homework 5 situation, but open addressing, we would need to do that. Okay. Or if we were doing quadratic probing, we might need to use a different kind of power 2 or a prime value for the table size. So depending on the kind of probing strategy we're using, the resolution might be a little different, but it's usually done when we resize the tables. Okay. Okay. So here's just for homework 5, a hint or reminder. So if you were to just copy this stuff over in your rehash into new function, things are not going to work, right? Because you're not going to be able to find things the way that you found them before. Okay. So you basically have to go one by one through all of the keys in your current table and then rehash them into their new locations, of course, along with their values. Okay. So you'll see some documentation on that in your homework 5 on Canvas, and also I think in the code the starter code that you have. Let's see. So full solution. So I worked this up, but I'll just tell you quite honestly, there's a lurking bug somewhere in my code, and I suspect it's in my tombstone cleanup code. So I'm embarrassed to say it, but it's a little bit of a nasty one. I haven't tracked it down yet. But if you want to see something that's working, for the most cases, it's sort of failing for my stress test. It's actually not a ton of code, and it's nice to see one of these things fully implemented from scratch. So you're welcome to do that. But the idea with this particular implementation is we're going to just calculate histogram of some very, very large word files. So for anybody contemplating the full homework 4 Wordle, end of semester project, you might want to come back and take a look at some of this code for use of histograms. But you don't have to. But the idea is, like we saw in our lab last week, we'll have a kind of a bucket for the words and a bucket for our frequency counts. And we're just going to read in some really big files and just try to count how many times we encounter each of these words. Okay. And we can kind of delete and re-add for stress tests to kind of see if the tombstones actually hold up okay. But I think that's where we have most of our problems. So this is a kind of collection of data members we'd want in our class. We're going to keep a constant track of the load factor. And for statistical and interesting reasons, we'll keep track of how many buckets we have, how many buckets are used, how many tombstones. And this is going to just be our dynamic array of buckets. So this is a pointer to a string, which means it's essentially going to end up being an array of strings, okay, or array of individual string instances, okay? So it's a pretty stable way to load up a whole lot of pointers, okay? A dynamic array of buckets, each holding a string. Sorry, not pointers, just a string. So each one of these will have a word, and then separately we'll have a counts bucket, right? So here's our dynamically allocated array of counts, okay? We'll keep our probing constant here and a largest prime here in case we use our quadratic probing method, okay? So those are kind of the high level things. Here are all the methods. Some of them are going to be pretty similar to what you'll see in homework 5. I'm I'm not going to take you through all of this stuff, but you should recognize some of this stuff from our lectures. GDC, find relative prime. There's a few utility functions in there, our hashing function, calculating load factor, etc. So the rest of these are basically our abstract data type methods, right? Does my table contain something? Finding a key using probing, all that stuff. So there, just for your reference, Ken, you don't need to worry about that on any tests or anything as far as the code is concerned, but I thought I'd throw that out there for you. Okay, and the link is there for you to grab. I think I have a pro, because they have data files. This is a Program IZ Pro link, so you'll have to have your pro account to change it, but you can certainly look at it and run it if you like. And then there's just a legacy replit link there as well. Okay. So there's our methods. And another thing I just wanted to throw out here, here's a little bit more C++ trickery here. So this is a hash function that is part of the library. So we can call the C++ hash function and use a template to say, we're going to give you a string. So this is their hashing function in C++ that's been written. And we can essentially drop in a string as long as this data type matches this data type, okay, and get something back out again. Okay, and it's interesting to compare what the difference is, right? If you have very minor changes to a string, it should actually hash to a pretty different value if it's a really good hash, and it probably is a pretty good hash. So if you're ever curious about just incorporating sort of a more bulletproof hashing function that's been tested in the library, you can do that via this templated hash function that's there. Okay. Which is maybe a little bit hard to find. Okay. So you can kind of see the difference that we get. Now, a couple other miscellaneous topics that have come up. I'll try not to butcher this one too much, but somebody asked about this. So we often hear about denial of service attacks. And so the internet, the web, basically the World Wide Web is, allows us to type in a domain name and have it mapped to a server. And the server is really many servers that these requests get mapped to. And so generally they redistribute the load, the request load, over many servers. And those servers are kind of like your buckets in your hash table. Okay. And these little links here are kind of like the requests that are lined up. It's like a jobs list that needs to be processed for each one of those buckets. So denial of service attack is one in which it figures out how to overload a specific server, right, with lots and lots and lots of requests. So if it were possible to figure out how the request got hashed to a particular server, we could potentially overload that server and sort of bring down the system, right? And this used to be a pretty common thing back in the early days when these servers weren't relatively hardened, right? So one of the things that we'd like to be able to do is make these hashing functions kind of hard to predict. So we don't want somebody to really be able to predict where something's going to go based on a minor change to a key. So reverse engineering these hashing functions would be a bad thing in general for these kind of situations. So very often what we'll try to do, and somebody did ask about this, is incorporate what's called salting the key. So if someone gives us something that they want to hash into a table, what we do is we add some secret offset value or some secret word to that key, and then we go ahead and hash that. So from the outside, it would be very difficult for somebody, or even more difficult for somebody, to sort of reverse engineer our hashing function. Okay. So if you ever hear about the reference to salting a key or salting a password, that's generally what we're doing. We're adding some secret item to every key that we're hashing before we put it into our hash function. So people can't sort of look at the input maybe and compare the output and try to figure out what our hash function is doing. So it keeps that a little bit more secure, essentially. Okay. I just wanted to mention that briefly in case anybody's kind of heard of that before. Okay, so summing up, let's just sort of take a look at the analysis on our good old, doubling of our array. So we talked about this quite a long time ago. We always want to double the size of our array so that we minimize the number of times we're rehashing. And if you remember, it's basically a geometric series. If we add up all of the work that we have to do at each doubling step, right? Not at every step, but at each doubling step, we actually end up with 2n on the order of 2n cost for doing that update, okay, which is essentially linear. So we can kind of keep ourselves in the linear space by doing that doubling. So what we did way back earlier on for our array implementations of lists and queues is the same here for our hash tables. Okay, so we're going to always try to double to avoid that. Now, what about resizing our table? When is it time to resize? So if you're doing separate chaining, like we're doing in homework 5, we want to be tracking our load factor, which is going to be the number of keys stored divided by the table size. Okay, so not the number of buckets used, because in separate chaining, we're going to have a lot of keys per bucket potentially, right? Because you're going to have a linked list. So it's total number of keys stored divided by the table size. Okay, so if we find out that our load factor, our LF, is greater than 1, that means on average, we're starting to have more than one thing per bucket, and we're starting to lose some efficiency. Now, it's okay to have more than one thing per bucket because nothing's going to be kind of perfectly evenly distributed across our table. But on average, if the average exceeds 1, that's the time we want to start thinking about doubling our array size. And if you think about it, that's because we only pay a one-time cost to hash to find the bucket. And if there's an overflow, we just sort of have a relatively short linked list there that allows us to quickly find something with one or two seeks of our linked list. So doubling when the average length of the chain in each of our buckets is greater than 1, that's the time when we would want to double. Okay, so in a situation where we're doing separate chaining, load factor is essentially the average number of items per bucket. So that's an important fact to keep in mind. Load factor for separate chaining is synonymous with the average number of items per bucket. Okay, and if we go the other way, if the average goes down to like 25%, in other words, every fourth bucket has something, or, because obviously you can't have a quarter of an item per bucket. But basically on average, if it's less than 25%, then that's a time to shrink our table because we're probably just wasting space. Okay. So that's for separate chaining. In open addressing, it's a little trickier. So without going into all the detail about why, remember here, again, our load factor is still number of keys over the table size. So it's the same definition for both of these, number of keys over table size. So if we're greater than 0.7, that means we're at 70% full, okay? And so that's the time where we need to double the table size, okay? If we're less than 20%, then it's time to shrink, okay? Because we're just wasting space potentially, okay? So same definition for load factor, just some different rules for when we actually got to deal with doubling the table, okay? Questions on that one at all? Okay, these questions do come up. These values sort of float around. Sometimes it's 0.25 to 0.75, depending on where you're looking, but that's generally the range at which we would do that. Okay. So let's see. So given a uniform hashing function, the average number of keys per bucket is going to be the load factor, right? So that's a fact we should keep in mind. The number of probes needed to insert is going to be proportional to that n over n, okay? So this is in separate chaining, okay? So it kind of makes sense if you think about homework 5, when you have to insert, if your load factor is 4, then you're going to have to search all the way to the end of that 4-length chain to make sure you don't have a duplicate. So that means your number of probes, even though it's seeking down a linked list, we're not probing in the open addressing way. That's going to be how many times you have to jump across the pointer in homework 5. Okay, so that's going to be proportional to your load factor. Okay, so keep that in mind. Okay, and so our optimal table size to maintain that is going to be really, you know, 1 or, as low as 25%. So we wouldn't want to get above 1 on our load factor. Okay. So I think I said that the right way. So yeah. And let's see. And so essentially, if we keep things in balance, we should average out to constant order in finding something. In other words, no matter how many items we have, with table balancing, we should be able to get to constant lookup, which means we do very, very little seeking inside of our probing inside of our open addressing implementation. Okay. So that's the nice part about this particular implementation. Okay. So we'll maintain a maximum load factor, like we were saying, and at any time we exceed that, we'll double our table size, and that should maintain our constant lookup cost. Okay. And I think we looked at some of those numbers a little earlier on. Okay. So performance for open addressing, okay, assuming we have a uniform hash and assuming we rehash around 50% load factor, is going to be constant, right? So it's never going to grow regardless of, on average, right? Our average time is constant no matter how many items we have in our table. There will be worst case performances where we have that really terrible long probe, where we might get to something on the order of n probes in an open addressing scenario. Okay, so the kind of questions you tend to get asked are, what's the worst case scenario for insertion? Well, we might have a really, really long probe in a relatively full table, and so that could take a while to find it, right? So if I have n things in the table, I might probe n times, okay? But on average, I should have the benefit of that 50% load factor and find it pretty quickly, okay? But it's nice that this is why these hash tables are so popular, right? On average, we actually get it pretty quickly, okay? So here's an example of that worst case, right? So just so we know, right? So here we could basically hit every single key through probing, trying to figure out where the 6 should go, right? And then we finally figure out a place for it because we haven't found it so far. So we hit every single key. We hit n of our keys along that probing path. So that's really what we're talking about there. Okay. And there's the big table. So of all the things we've looked at, sequential searching, right? That's going to look through everything always, right? Worst case scenario. On average, we might get lucky and find something right off the bat. Binary search, we said that was basically a log n because we're doing a divide and conquer. Worst case in an unbalanced binary search tree, right? It could be really badly unbalanced. But if we balance it, we kind of get a log n kind of performance, and that's good. That's better than an n, okay? And so these are our worst case scenarios, right? So balanced binary trees are actually really preferable because it limits our worst case scenario to a divide and conquer kind of thing. That's pretty good. Okay. We can have a bad day with separate chaining, and we can have a bad day for open addressing. But on average, we have a constant value of 3 to 5 cost for searching, inserting, and deleting, right? That is what's really popular about the hash tables, okay? Both separate chaining and linear probing, okay? And one of the costs we pay for that is we cannot print things out in any alphabetical order. So we sort of gain this performance speed on average above a binary search tree. So we're faster than the binary search tree on average, but we cannot print things out in order. Okay. So our key value storage is more like, our serial numbers or license plates or something like that. Okay. So that's kind of a high level view and really a wrap up of the kind of this whole part of the course so far. We've really been looking at, started with sorting and searching, and kind of have come through all of these different data structures. Okay. So a lot of the times we choose the data structure based on whether or not we need ordered or not ordered. And that's the big dividing line. And then we figure out, okay, how often am I going to be inserting? What are my memory costs? Do I have to worry about, searching through really long chains, that kind of stuff. Okay. So that's kind of a wrap up on that. I think then that's kind of where we've spent the last 2 or 3 lectures, just to kind of make sure we're all on the same page. And remember that big theta, this does come up. So big theta means it's tightly bound, right? So big theta is something that means that the worst case and the best case would be tightly bound. Okay. So it's actually not true of these two, that the worst case and the best case is tightly bound, because we actually have n over here and we have constant over here. So it is not a big theta, actually. It's is not tightly bound. We would say this is tightly bound. Okay. Okay. I think, yeah, hopefully I didn't make that too unclear. Let's see. And this is just some extra stuff for folks who are interested. Given n slots and a uniform hashing algorithm, one of the common questions that's asked is, how many items can we store in our hash table before we expect our first collision? Okay. And there's some interesting research that that is behind this, but basically it's about the square root of pi times n over 2. Okay. So we can calculate the probability of that first collision based on the number of things we've stored so far, which is kind of fun. Okay. And the longest number, what is the largest number of collisions on a single slot after storing an item? So there's all sorts of kind of interesting equations that we can pull up to calculate these probabilities. Okay. Now, notationally, going forward, if you see us using ln, that is the natural logarithm, which is really just log based e. For those of you who have not seen that notation before, we'll see a few more notations that are used in our performance calculations that use the natural logarithm. So just keep that in mind. If you're curious what that is, it's like, instead of saying log base 2 or log base 10, it's log based e. Okay. Okay, and I'll leave you with that. Last few reminders, our hash table is a data structure. It does not support ordered operations. It does not support duplicates, and is comprised of our slots or buckets. And we use hashing or a hashing function to crunch our key into some kind of index. And separate chaining and open addressing are our 2 primary approaches. Okay. And if we're doing open addressing, we need to worry about cycling to avoid infinite loops. And I think that's it. Now, I'm not going to go through all these, but we've talked about all of these questions, and these are typical questions that might come up in a quiz or test or an interview. So you should be able to answer them. But even if you can't, you could have a conversation with ChatGPT, or you can look back at our notes to cover some of the stuff that we talked about. But my guess is it'll ring a bell for you. If not right away, it'll probably do so after you kind of do a little bit of digging on it. But all of these are pretty straightforward questions that you should feel pretty comfortable about. Okay. So I'll leave you to those to come back and review. Um, and just a couple ideas for you. This is not an assignment, but we're going to try to incorporate this idea of dynamic programming at some point before the end of the semester. We haven't done this before, but here's what we're looking forward to. And it's one I just want to throw out so you can kind of think about it. If I have an array of 7 values, and I would like to find a way to add these things up to 53, right? What are all of the sums, or bigger than, what are all the sums that I can produce by combining these numbers to come up with that, right? So if I say print all sums bigger than our target, okay, so the array of size 7, my target is 53, how would you go about writing that program, right? So you can pick 2 things or 5 things or 4 things. So it's a little bit not obvious how you might go about that. Okay. So interesting food for thought. A couple possibilities. You could have a bunch of nested loops, right? So, but if your array was size 1,000, that means you have 1,000 nested loops. You could try to do the same thing with recursion, but if you did those things, what kind of performance do you think you would get? So this is a classic, sometimes referred to as the coin problem. You got coins in your pocket, and how do you combine them in a way to pay for something exactly? So we're going to look at how we take that problem and turn it into what is potentially an exponentially expensive problem into at least a quadratic performance problem, worst case, which you might think is not great, but exponential is really bad. So if we can kind of simplify that with this technique called dynamic programming, we can find solutions to these problems quite a bit faster. Now, if it was a national election year, what we usually do, and what we did last year, was we ran simulations on all the possible ways that one or the other candidate could reach the required number of electors. So if you know about this, every state has a certain number of electors. And if one candidate wins enough states to cross some threshold, some target value, they get to be president of this country, right? And so it was a quite interesting burning question. And if you've ever watched the returns on voting across the country, they're running a dynamic programming solution to figure out who the most probable winner is and whether or not the chances of someone else overcoming them is getting so narrow that it might not be feasible for them to win. And that's very much what's happening whenever these things are being done. So even with our redistricting, sorry, not to be political, but our redistricting question that's coming up for the state of California in the next week is all about whether the combination of districts add together enough votes, if they're combined in certain contiguous ways, to maximize one party's advantage or the other. So the combination of these different regions that are next to each other is a dynamic programming problem. How do you combine them in ways such that one party has the upper hand? That's a dynamic programming problem. Okay, so this is one of the reasons I just wanted to introduce this right now, so we have a real world example, and we'll know, sometime next week what the answer to that particular vote was. But it is a problem that we want to be able to solve really, really, really fast, especially for things that are even more complex than, the number of regions in the state of California. Okay, so we'll try to look at that. And then separately, Lab 20, I think this one's self-explanatory. I'll let you guys dig into it if you want to. But basically, we have this function called delete every kth node. So let me just show you this briefly. So it's a relatively famous problem. You can look it up. It's the Josephus problem in Wikipedia. And I've kind of laid it out for you in Program IZ there. But essentially, if you have this data structure where you have a pointer to a head node, and your rings it's all double linked forward and backward, and I give you a 4, then your function should count 1, 2, 3, delete the fourth one, and then close up the gap. Okay, but then it should go forward 1, 2, 3, 4, close up the gap. 1, 2, 3, 4, close up the gap. Go around until you are down to one item. So even with 3, you're going to go around until you've counted 4 and then delete that. And then we go back and forth until we count 4 and delete that. So the thing that you return at the end of your function, if you decide to do this, should be pointed to by the head, and its previous and its next pointers should point to itself. Okay, so that's, if you can get to that state for k equals 4, then you know you have done it correctly. Usually it ends up crashing before you get there on your first or second try. So this is our optional lab. So you can do that. Again, you can do that at any time. It's just a good skill builder. And you should find that on our lab 20 for today. Okay. Any final questions before we call it a day? Okay. Thank you, everybody, for your patience. Hope you guys have a good weekend. I'll see you on Tuesday